And the final operation is first true. So it's actually two operations combined together. There's checking if there are any elements that are true and finding the position of the first one. The reason they are fused together in one operation is that because you can't really find the position without checking that there wasn't any. There was any. This is, however, not the only design choice. This is, for example, from a different SIMD library called VC, and they do any and then, first one, right? And do it separately. They don't return an optional from first true. So we're going to start with finding the position because it makes explanation easier. All right, so the way finding the position is done is you take the mask, logical, right? And you convert it somehow into an integer. And then you find the first bit set, right? The first bit set will be from the end, from the lowest bits, because we are on little engine systems, right? And it means that the last bit corresponds to the first byte set. Okay. So how can we convert from a SIMD register to bits, right? To some form of bitmask. It's actually quite common operation, so this is why in Eve we have a special class called top bits, and we can just construct top bits from a mask, and it will have some number of bits per element, right? So here it's just 1 bit per element. On x86, this is very simple. We have basically, if we have IVX512, then it is already a bit mask. Before IVX512, we have special instructions called move mask. There's a version for a byte, for 4 bytes, and for 8 bytes. 8 bytes. And there's not a version for 2 bytes, so for 2 bytes we use the 1 byte version, right? So for example, this was for 1 byte, right? And if we use uint16 here, we will get the same result but 2 bytes, right? Okay. For ARM, there is no such instruction. So let's see how we can do it, for example, on ARM v8 for chars, right? So let's say we have 16 chars. I only drew 8 chars. Imagine that there's another 8 here, right? Okay, let's interpret them as shorts and shift right by 4. What it will give me is that now I have, instead of having 8 bits per char, I have 4 bits per char, and 8 byte bits of whatever zeros. Then we can convert this to chars. Like what this will give me, it will give me 8 bytes worth of chars. Right. 8 bytes worth of chars on ARMv8 is good enough because ARMv8 is a 64-bit architecture. Okay, and if we actually look here, this is top bits for ARMv8. Shift right, convert to chars, and gets a 64-bit number. Good stuff. On ARMv7, unfortunately, there is an implementation, obviously, for top bits, but for chars, it's not very good, right? I have tried to come up with a better solution. I failed. Luckily for us, this is only done once. The whole first true is done once per loop. Like if we look here, in the loop, we only do any, and then at the end of the loop, we're actually going to convert to the position. Okay, yeah. So how to do any? Well, on x86, we can just use top bits. We got to the integer in one instruction, we can test it and then move on. Right. On ARMv8, those was like 3 instructions. We can do better. The way we can do better is we can realize that effectively what any means. Any means is we're checking that any bytes of our logical is not 0. Right? It means that maximum in whatever type we want is going to be non-zero if any, for any to be true. And there is a horizontal reduction that in one instruction takes our 16-byte register and returns us a maximum U32. And if that maximum is not 0, any is true. Should be fairly clear. On ARMv7, things are again not so great. For one thing, on ARMv7, like, it's a 32-bit architecture, so we need to get down to 32-bit number. On the other hand, the support for chars is even worse. It's pretty bad, right? Not even worse, but pretty bad. So what we can do is we can first take our logic, right? And there is somewhere we're looking for a byte that is FF, right? Out of 16. Well, let's compare that to 0, but only is E32, but is as integers. Then we will get the whole where there was a byte that was not 0. We're gonna get 4 bytes that are not 0. And then we can do whatever we do for integers, right? So we can convert that to 8-bit number, and then we can convert that to for 8-byte number, and then we convert that to 4-byte number, and then we get the result. So it's not, trivial, but it's okay, I hope. I actually don't have the ARM benchmarks. And with this, let's have a look at some of the things, some of the architectures we didn't touch, like that EVE doesn't really target. So first of all, there's PowerPC. EVE targets PowerPC a little bit, but there are 3 versions of PowerPC. There's Power 7, 8, and 9. They are pretty powerful and fairly reasonable, but it's just a lot of effort, and it's unclear that there's actually enough use case for us to try to do it. There's WebAssembly. WebAssembly is very interesting because on one hand, it will run on either home desktop, a home laptop, or a phone, right? That's where WebAssembly will run. And those will give you really good SIMD intrinsics, right? So it will likely be, WebAssembly is 16 byte, right? So it will likely be SSE 4.2 or RMv8 under the hood, right? When it's all said and done. However, we have to write them, right? We know what we would like the code to look on SSE 4.2. We know we would like the code to look on RMv8, right? But we need to write them through the common layer of abstractions of this WebAssembly SIMD stuff, so that it presumably will generate some okay code for those. I don't yet know what it will look like and how the measurements will come out. We'll see. There is ARM Helium Instruction Set. This is a new instruction set for embedded ARMs. Right. For some reason they didn't use Neon. There are some explicit reasons why they didn't. Looks fairly reasonable. It's just work to target ARM Helium. Seems like should be doable. And finally, there is ARM SVE SV2 extensions, and these are weird. So this is ARM's AVX, right, or IVX 512, whatever. This is for now. I only heard of computers like this in supercomputer sector, right? The interesting part about them is that you don't know the bit widths of the register. So you don't know it's going to be 32 bytes register or 64 byte register. We know that it's going to be at least 16. That's guaranteed. And not knowing the register widths makes programming a lot harder. We don't really know how to program them in abstract. The way I saw it's done so far is that people they just know what the register width is, and they compile for that. So they will say, okay, so my register width is the instructions generated will not know the register width, but the program will. The reason, by the way, they don't knowing the register width is so that they don't have to write a new spec, right, for 32 byte registers, for 64 byte registers, right? If you were thinking about the 128 byte registers, that's, I don't know, maybe, but it's not very likely because it means you would have to have 128 byte cache line at least. You can't really have a register, as far as I know, bigger than the cache lines. It kind of doesn't make sense. But anyways, so So they would so there's extensions and there's GCC extensions to say, hey, my register is my SVE is like, whatever number of bytes that you want. And another thing we can do if we need to really target a few of those, well, we can compile a few versions and then load dynamically the version of the library that compiles for SVE with 32 bytes over the SVE with 64 bytes. This is probably some directions that ETH is going to go with respect to SVE. Whatever you do, you may be able to put the algorithm, maybe your algorithm will work in just without knowing the register widths. And anyways, that's it for today.